All right, Unit 7, Organic Chemistry. This will be the last unit of the semester. Here we have 3 organic compounds you may have heard of: sucrose, regular table sugar, caffeine, my drug of choice, and acetylsalicylic acid, better known as aspirin. You'll see this on a few of these slides, not needed, just some background information or just something off to the side. I thought I'd give you a little bit of a preview of what you're going to be asked to do at the end of these notes. Given a name like this, you will need to be able to draw a structure like this. Fundamentals of organic chemistry. An organic compound is any compound containing carbon except carbon monoxide, carbon dioxide, carbonates, and carbides, which are binary carbon metallic compounds, such as calcium carbide. You don't need to concern yourself with this very much. You're not going to be seeing these, but they do contain carbon, but they're not considered organic compounds. And by the way, organic compounds, the term organic comes from the fact that once upon a time it was believed that only living organisms could produce these compounds. But we now know that we can synthesize it in the lab, but nature has us beat big time. Why carbon? Why is carbon so special? Well, if we notice its placement on the periodic table, it is a period 2 element. It's a very small element, and it's the first element that has 4 valence electrons. Now here's a little blurb on why carbon is so special. You can abbreviate this in your notes as needed. Carbon is a very small element with 4 valence electrons, each capable of forming very strong covalent bonds with other carbon atoms and other elements, most notably hydrogen, oxygen, nitrogen, and phosphorus. This allows carbon atoms to form very large and complex molecules. Kind of the granddaddy of all complex molecules is DNA. Carbon-carbon bonds are what holds it all together. And just to give you a sense how huge molecules can be, in a DNA molecule, and it is called a molecule, contains about 204 billion atoms. Hydrocarbons, compounds containing only hydrogen and carbon, as the name implies. Here are some examples. Plastics are all hydrocarbons, though there'll be other elements as well. Motor oil, diesel, gasoline, just to give you a sense of a few hydrocarbons that you may have heard of. Due to the complexity of compounds that can form, organic molecules require a very specific naming system, which is referred to as nomenclature, and structural formulas. So for example, you don't need to write this down, 3-methylhexane, we'll be getting to these kind of names and how we read them, has this as its chemical formula. And here is the actual molecule being rotated around. Now notice that every carbon is bonded to 4 other carbons, and it's bonded in a tetrahedral shape. Remember that shared electrons around a central atom move as far away from each other as possible, as per the VSEPR model. Now we draw it in a 2-dimensional kind of straight line like this, but every carbon, all of the bonds are tetrahedral. Recall the Honk rule. Hydrogen are halogens, oxygen, nitrogen, and carbon. And the order of the name Honk tells us what the number of bonds that we would typically have for those elements. Hydrogen will always have 1 bond. Halogens usually 1, but can have more than 1. Oxygen will have 2 bonds, nitrogen 3, and carbon 4. So our focus is on carbon. So any of the molecules that you'll be drawing, looking at, every carbon will either have 4 single bonds, 2 single bonds and 1 double bond, 2 double bonds, or a single and a triple bond. There will be no exceptions to that. 3-methylhexane, heptane. So these drawings, as you can see, better represent that tetrahedral shape that we have around each of the carbons. Okay. Both of these have the same molecular formula, C7H16, but you can see that they are different structures. So molecular formulas, remember, tells us the smallest whole number ratio of atoms that we have in a molecule. But in organic chemistry, just like a Lego set, you can put together the pieces in many different ways. And so these, though they have the same number of atoms and same types and number of atoms, they are different compounds, have different chemical and physical properties, and as you can see, different names. Let me mention before I go, this tetrahedral shape that we have around the carbon, we're going to say goodbye to that and draw it in a much easier way. But don't forget, we have this zigzag shape between each of the carbons in reality. Skeletal structures have just the carbon-carbon bonds, where anything else that might be bonded to the carbon is removed. And this will be quite helpful when we draw structures later on, if we first just connect the carbons. It's called skeletal structures. Okay, types of structural formulas. Okay, so these are the three types of structural formulas you need to be able to read, if not draw. This is expanded formulas where all bonds are shown. Now you can see sometimes we have to draw the bonds a little bit longer just to fit in everything else. It doesn't mean that we have longer or shorter bonds. Skeletal formulas show only the carbon-carbon bonding. And again, this is quite advantageous when we draw structures to first start off with the skeletal formula. However, condensed structural formulas will be what we will be using, where all bonds are drawn except carbon and hydrogen. So the CH3 that you see here, well, that's exactly the same that you have here, CH3. It's just we've drawn it more compact or condensed, as we say. So CH2 is this CH2 here. So you can see that the line is kind of drawn through the hydrogen, but it doesn't mean that the hydrogen is bonded to the carbon. The carbons are what link the entire chain together. Okay, we will be using this method. You will be given often these other methods, and you need to be able to interpret them, but this will be the method that we'll be using when we draw our structures. Formulas can be condensed even further. So this is the structure from the previous slide. We can condense this down even more. So this CH3 here, rather than drawing it as a bond like this, you can see that all the bonds have been removed and this CH3 is squeezed in here with parentheses. Notice that you have three CH2s here in a row. We can compact those together here. So those three CH2s are now here. Okay, but use this. However, we will be getting to these other ways of writing structures later on in the unit, but not for right now. Note, structural formulas might be given so that the bonding is more apparent. So for example, if we were to have this as our condensed structural formula, you might see it written like this, where the hydrogen is on the other side of the carbon. And this really gives you a better visual of what's being bonded. Do not do this yourself, just be aware that both mean the same thing. In recent years, IB has started using this more in the problems that they give, but they both mean exactly the same thing. Again, you will be writing your structures like this, but when you see this, it's not a typo. Hydrocarbon classifications. There's three types of hydrocarbons: alkanes, alkenes, and alkynes. And I'll walk you through each one right now. An alkane contains only single bonds. has the general formula CnH2n plus 2, meaning that, let's say that N was 3. Well, then the number of hydrogens would be 2 times 3, which would be 6, plus 2, which would be 8. So if you have 3 carbons, you have 8 hydrogens. An example, propane, the one I just rattled off. Now the ending of the name, ANE, comes from the fact that it is an alkane. There's only single bonds. An alkene has one double bond. It'll have the general formula CnH2n, so we've lost 2 hydrogens because we now have that extra bond between the carbons. Example, propene. So you can see that this carbon had 3 hydrogens, this carbon only has 2 because now it has another bond that it needs to contend with. Now the name of this ends in ENE because it's an alkene. So alkane ends in ANE, all single bonds. Alkene ends in ENE, has one double bond. An alkyne has a triple bond. It'll have the general formula CnH2n minus 2. We lose 2 more hydrogens because we, again, have another bond. The name of this is propyne. The ending YNE tells us that it is an alkyne and that there's a triple bond in that molecule. Alkanes are called saturated hydrocarbons because they contain the maximum number of hydrogens possible. Both alkenes and alkynes are called unsaturated hydrocarbons because we could, if we broke one of the bonds, we could add more hydrogens to these molecules. We'll be talking about reactions like that at the end of the unit. Now these formulas, these general formulas, are quite advantageous if you were asked to identify the type of hydrocarbon. If you were to look at a chemical formula and see that you have exactly twice the number of hydrogens as carbons, well, then that tells you that it's an alkene and that somewhere in the molecule it has a double bond. So these are quite helpful. So I would box those and file that away. Naming hydrocarbons, again called nomenclature. All elements and compounds are named using the IUPAC naming system, which stands for the International Union of Pure and Applied Chemistry. This is the worldwide organization that's responsible for all chemical compounds, elements, the names of it, the properties, all of that it's kind of a registry of information. If you go to iupac.org, you'll find a wealth of information about compounds. This system ensures that every compound is given a unique and unambiguous name excuse me, that correlates directly to its structures. So these 4 guys, they have similar names and they're similar, but you can see that they are unique. Each one is unique and special in its own way, just like organic compounds. The names might be similar, the structures might be similar, but they're different. They're unique. Prefixes derived from a mix of Greek and Latin numbers are used to indicate the length of a carbon chain. So these are the 10 prefixes that we'll be using. It goes beyond 10, though this is as far as we will be going. So if the chain is just 1 carbon long, it would be meth, like methane. 2 is eth, 3 is prop, a bute is 4, and that's a long U. It's not but, it's bute. Pent is 5, hex 6, hept 7, oct 8. Non is 9, and it's a long O, known, not non. And 10 is dec. So these are going to be very important in naming our compounds. Straight chain alkanes. Now the name straight chain is a bit deceiving, though we do draw it as a straight chain. But remember, around every carbon, the bonding is tetrahedral. And so this really would have a zigzaggy shape. but for simplicity's sake, we draw it in a straight line, and it's referred to as a straight chain. Now the name of this is pentane. Pent because it's 5 carbons long, and ane because the carbon-carbon bonds are all single bonds. It's an alkane. Branched alkanes. This would be an example of a branched alkane. So you can see that one of the interior carbons has something bonded to it. Now to name it, we first want to identify what's called the parent chain. The parent chain is the longest carbon-carbon chain. And this is our branch. Hydrocarbon branches are called alkyl groups. Now you can have other things bonded to the carbons, as we'll get to in subsequent notes, such as oxygen or a halogen. But if the branch is just a hydrocarbon, then it's referred to as an alkyl group. Now where is this alkyl group on the chain? What we use are numbers. We number the parent chain so that we can identify where things are bonded, where the branches occur. So to name this, we name it 2-methylpentane. 2 tells us that off of the second carbon in, we have our methyl. So we separate the number from the name with a hyphen. The YL comes from it being an alkyl group, which is a hydrocarbon branch. And there's no space. Very few organic compounds that we'll be looking at, none today, will have a space in its name. Okay, now you have to be a little bit careful. These structures that are drawn here look like they're different compounds, but they're really exactly the same, just one is flipped over. So, and that's the model that's being represented here. So as you can see, let's wait for it to get over here. So now you can see that it's off of the second carbon, like down here, and then now it's off what looks to be the fourth carbon here. But both of these are identical, and both of them are 2-methylpentane, the one that we just looked at in the previous slide. So warning, you might want to name this 4-methylpentane, because here in the West we have a bit of a prejudice, a bias of going from left to right. So we would number this 1, 2, 3, 4, but oh no, no. Always number the parent chain from the carbon that gives the smallest numbers. And so numbering it from the left, this would be carbon number 4, but numbering it from the right, it would be carbon number 2. And that's what we would want. Always number the parent chain from whichever direction gives you the smallest numbers. So again, the name is 2-methylpentane. So let's practice. Now in naming this compound, first we identify the parent chain. Not always quite as obvious as you might think, as we'll get to a little bit later on. So numbering it, we can see that off of carbon number 2 and 4 we have methyls. So to name this, we go 2, 4 hyphen dimethylpentane. Now that di is a prefix that we are going to add when we have multiple branches that are identical. So for multiple identical branches, use di, tri, or tetra. It won't go any further than that. So either 1, or either 2, 3, or 4. Now you might say, well, why don't we just name it dimethyl? Why do we need the numbers? Because we need to say where they occur. Now for this one, we number our parent chain, and we can see that we have a methyl off of carbon number 2. Meth, remember, means 1 carbon. This is 2 carbons long, and so this is eth. Sometimes students want to say that this would be dimeth. because there's 2 carbons. No, it's 2 carbons long, so it's ethyl. Methyl, ethyl. Now to name this, it's a little different than, a little surprising perhaps. We name the alkyl groups in alphabetical order. So eth is alphabetically before meth. So even though the meth has a smaller number associated with it, we name the ethyl first. So to name this, it's 3-ethyl. Off of carbon number 3 is where we have the ethyl. And then carbon number 2, we have the methyl. And it's a 5-carbon chain, so pentane. Okay, now the numbers and names are separated by hyphens. So whether the name is after the number or even before the number, we use hyphens to separate it. Again, notice there's no space. Now this one is a bit deceiving. The ones I've been showing you previously, I was a little bit more explicit on what the parent chain was. You might want to think that you have a methyl here and an ethyl here, but this is really just part of the parent chain. Remember, the parent chain is the longest single carbon-carbon bond. So even though it wraps around like this, it's just like a chain or a rope. You can just kind of bend things around as you might want. So this is our parent chain. To redraw it, the way that it would be more typically drawn if you were asked to draw it. So these are exactly the same thing. So this is 2-methylheptane because it's 7 carbons long. Okay, now for this one, after you've drawn it down, see if you can circle the parent chain. Remember, it's the longest carbon-carbon chain. I will do it in 3, 2, 1. So this is our parent chain. Now, on the parent chain, we have 3 methyls and 1 ethyl. To number the parent chain, remember we number from whichever side gives us the smallest numbers for our branches. So if we were to number it from the left, off of carbon number 1, 2, 3, 4 is the first carbon that has something bonded to it, but numbering it from the other direction, 1, 2, 3. So we would number it from the right because that gives us smaller numbers. So 1, 2, 3, 4, 5, 6, 7, 8. Now to name it, we have 3 methyls, so that's trimethyl. But remember, we name ethyl first because it's alphabetically before methyl. By the way, the di-tri-tetra is not a consideration when we name things in alphabetical order. So to name this, it's 5-ethyl, and then we have 3 methyls. 2 are off the same carbon. 1 is off of carbon number 5. So 3, 3, 5 trimethyl. So note the convention here. It's very, very fussy. A hyphen between the number and the name, another hyphen, and then the numbers are separated by commas. And even though we have 2 carbons or 2 methyls off of the same carbon, each one is given its own number. Remember, the IUPAC naming system that we're using is very explicit on exactly what's going on. There might seem to be some redundancy involved, but that is the system that we're using. And then the parent chain is 8 carbons long, and so that's going to be octane. So again, no spaces. FYI, that last one was an example worked out in your homework packet. Now, the homework packet that you have is a really nice, almost tutorial of how to do all the that I'm talking about here, how to name and draw structures. So please take advantage of that. Read through each one of the examples as you progress through the assignment. So this is the very one that we just did, and you can see that it walks you through step by step how to name it, and the name that we just came up with is down here. Now this, notice we have a double bond. So that means it's an alkene. The name will end in E-N-E. Numbering our chain, the name would be 2-pentene. So off the second carbon, we have a double bond. IB prefers this as the way we name it, where the 2 gets squeezed in between the prefix for the parent chain and the E-N-E ending. So this would be pronounced pent-2-ene, but we'll be using this. Now here we have a triple bond and we have a methyl group. So our name needs to tell us both where the triple bond is and where the methyl is. It's an alkyne, triple bond, numbering it. Now we first name the methyl. So 3-methyl and then 1-pentyne. As we'll talk about in a minute, going backwards in the name, the order makes a little bit more sense. So the YNE tells us that we have a triple bond off of a 5-carbon chain. Where is that triple bond? It's off of the first carbon. And then we have a methyl. Where is that methyl? It's off of carbon number 3. IB would name it 3-methyl-pent-1-ine. Now that IB way of naming it, you just need to be able to read that. So don't worry about that too much. It's fairly self-explanatory. Drawing structural formulas. Okay, so we're going to draw condensed structural formulas for the following hydrocarbons. So this is going in reverse. You'll be given the name and asked to draw the structure. Okay, so let's see, how would we go about naming or drawing the structure for 2,4-dimethylpentane? Okay, we first will draw the skeletal structure. Remember, skeletal structures are just the carbon-carbon bonds. Now to do this, big hint is to draw the structure by reading the name in reverse. So as I just kind of walked you through, if we go backwards, everything kind of falls into place. So we can see that ANE means that the carbon-carbons are only single bonds, and the parent chain is 5 carbons long. Okay, so we'll draw the parent chain first. So here's our 5 carbons. Now leave some room between the carbons to put in hydrogens that we'll need when we're done. Okay, so we have a 2 methyls. Where are the methyls? They're off of carbon number 2 and carbon number 4. And then complete by adding hydrogens so that every carbon has exactly 4 bonds. So this first carbon has only 1 bond, so it's going to need to have 3 hydrogens. This carbon has 2 bonds, so it's going to need to have 2 hydrogens. This carbon will need 3 hydrogens, etc. So that would be our structure. Double check that each carbon has exactly 4 bonds. That's the most common error, is putting too many or too few hydrogens on our carbons. 4, the magic number. Let's try another. Okay, let's try another one. You can pause the video, try it yourself, but I will walk you through it right now. 3-ethyl-1-hexene. So we'll first draw our structure, reading the name, or the skeletal structure, reading the name in reverse. So ENE tells us there's a double bond off of a 6-carbon chain. Where is that double bond? It's off of the first carbon. And then we have an ethyl off of the 3rd carbon. So this would be our parent chain with a double bond off the first carbon, and then 3 carbons in, we have our ethyl. And then now all we need to do is add the missing hydrogens so that every carbon has 4 bonds. And there you have it. Always double check that you have exactly 4 bonds. All right, that is it. End of notes.